All right, we are now recording. Okay, let me go over just a couple of minor announcements. As you heard when Dr. Briggs stopped by, the trip that, I think I told you this earlier, you may not have been here. Near the end of last term, I got an email from the National Science Foundation that they're running a special workshop. It sounded like it might be good for the school to participate in, but it was asking for a team from the school. But the National Science Foundation sent it to me, so I forwarded it up the chain of command and said, and they gave us three possibilities. Spelman College on a Friday, Saturday, Xavier College down in New Orleans, Spelman's in Atlanta, Xavier down in New Orleans on a Monday, Tuesday, and then someplace in the Midwest. And it was in the middle of the week too. So I emailed up the chain, including the vice president, and said I'd be interested in participating in this, especially if we could go to Spelman on Friday, Saturday, so it won't mess with any of my classes. Well, I got that day or the next day, got a phone call from the secretary that he needed to talk with me, and we went phone tag for a while. Finally, I got to talk with him. He said, well, we're trying to get the one to Xavier in New Orleans. I said, well, that's on a Monday, Tuesday. I've got classes Monday and Tuesday. Lots of classes Monday and Tuesday. And he said, well, I didn't want to mess up a weekend. So that shows the priorities. Instructors worry about classes. Administrators worry about weekends. So they requested Xavier, but he said, well, they may not give it to us. They may want us to go to Spelman, which I was hoping to. Nope, they gave us Xavier, and that's what that was about. I need to make my travel arrangements for Xavier. So, I can't remember when it is. It's not this coming Monday and Tuesday. It's the following Monday and Tuesday, I think. So that Monday, I will not be here. So next week, what we might try to do is make up the class sometime either on a Tuesday or a Thursday. I'll let you know Monday what might work out. Are any of you available after 3:30 on Tuesday or Thursday? Nobody? Okay. Well, I might have to just do the class to myself. I'd rather have at least a few students here, because it gets really boring talking to yourself for 2 hours and 40 minutes. But no one can make a Tuesday, Thursday, or Thursday, either one, after 3:30, because I have class that goes right until 3:30. Well, I'll probably record the class either Tuesday or Thursday, 3:30 next week. If any of you can make it, please let me know what your preference would be, and I'll schedule it for that day. And if not next week, then the following week will be there. I'll let you know. I'll find out when I make those arrangements. Okay, that's one thing. Second thing, I think I told you they finally said, I haven't seen it in writing yet, that they were going to pay me for an overload, which then meant that I had to change my office hours, because if you're here teaching overload, you have to be here extra hours. So that's why I'm here after 3:30 on Tuesday and Thursday, because that's when I'll make up the time for the overload. So what I told you at the first of the term, that I'd be leaving shortly after 3:30 on Tuesday, Thursday, it's now going to be 5:15 on Tuesday, Thursday. And the days I make up this class, it'll be even later, because to 2 hours and 40 minutes, not going to get there by 5:15. So I'll be a little later those days. All right. And so therefore, I've changed the syllabus. All the major content is the same. It's just my office hours are the only thing that changed. And I changed my locator card. So they're both out on Blackboard in the corrected forms now. Good. Any questions? Sorry that took so long. All right, we're starting 2.5 today, which is evaluating limits algebraically. Haven't we been doing that? Actually, we have. I go on and show you and let you do this. And, of course, what's the first thing we try? Substitution. What are the things you watch out for in substitution? If you can just substitute and it works, fantastic. two possibilities of not working. What would those two possibilities be? Okay, one would be something over 0. Something not 0 over 0. If you ever get that, what's your conclusion? Does not exist. The limit cannot possibly exist. It's undefined. You can't do it. Something over 0. What possibility may give you something? Zero over 0. That's called an indeterminate form. Now, back in math before now, anything over 0 you said was undefined. Something non-zero over 0, that's still undefined. You can't do it, impossible. But if you have a 0 over 0, when you do your substitution, you're not sure. That's an indeterminate form. It may be undefined, or it may actually give you a limit. So, when you're evaluating, try substitution first. If you get an answer, you got it. If you don't get an answer, if you get something over 0, no limit exists. If you get 0 over 0, you have to do some more work. And we'll talk about the more work later. Okay, so substitution is used to evaluate limits when the function in question is known to be continuous. Now, if it's a discontinuous function, and you're approaching that discontinuity, and it's not a removable discontinuity, it can't happen. If you're doing like this, no limit's going to exist at that value. It could back here, and it could over here, but not there. What kind of discontinuity do you see there? Let me blow it up for you. And I'll try to blow it up for you. There we go. This is really slow. I hit the button and absolutely nothing happens, so I hit it again, and then it happened twice. Okay. You see the discontinuity here? What kind is that? 3, 4 kinds of discontinuities. Okay, that's a hole. That's one way to call it. That's called a removable discontinuity. Assign a value of 8 to that, and you have a removable. So this would have a limit as you approach x equal 4 from the left, and from the right is both directions is approaching 8. That's a removable discontinuity. It's discontinuous there. You can't, you see this is a 0 over 0 form. Look at a 4 there. 4 squared is 16 minus 16, 0. 4 minus 4, 0. That's an indeterminate form. Okay. Now, we'll talk about how to do. They did it by graph, sort of the hard way. Can any of you think of an easier way to do that? May not be easier. An algebraic way of doing that. Factor the numerator. Excellent. Now, I can't write on this screen, so how do you factor that numerator? Let me get my pen activated. Boy, this is slow. Okay. It's really slow. All right. How do you factor that numerator? X plus 4 times x minus 4 over x minus 4. What do you see happening now? Yeah, you can divide out the x minus 4s. Now you can let x approach 4 without having a 0 in the denominator because you've lost your denominator. And what does that give you? 8. And sure enough, that's what the removable discontinuity told you. Okay? Since it seemed like we had trouble with removable discontinuity, what's this kind called? Jump discontinuity. Those, if you got that, that's never going to give you a limit. Okay? Another kind? It's infinite discontinuity. It's going to infinity. If it's going to infinity, it's never going to reach there because that's not really a number. That's an infinite discontinuity. And then you have some others that are none of the above. and usually they won't have a limit either. Okay, so it's only removable that will give you a limit. Okay, now we have just done what they're going to do. You factor that numerator, and you might eliminate it. And typically you can do that with removable discontinuities. Okay, if you try to take the limit as x approaches 4, substitution gives you that indeterminate form. Proceed and see if you can work that out. If it gave you 7 over 0, don't try to work anything out. It's never going to work. Okay? That is basically an infinite discontinuity. If you had a piecewise defined function that was approaching 4 from different numbers from different directions, that's a jump discontinuity. That will never work. There's always going to be a piecewise defined function that does that. Well, yeah. And then your other that is none of the above, that's usually a undefined form, 1 over x or something like that, inside another function. Okay? If that inner part is undefined, you can't define the outer part either. So that's a never type situation. So they jump to the the first example, but here's what I've been saying. If you've got your text, and this will be the new edition, I don't know if the old edition has it, in a block in the middle of the page or top of the page 85 or somewhere thereabouts, we say that f of x has an indeterminate form. What's that? Indeterminate? 0 over 0. Not 7 over 0, but 0 over 0. At x equals c, if the formula for f of c yields an undefined expression of the form, now it's not just 0 over 0, that's the one I've been telling you about, but that's one. That's called indeterminate. If you see something that's infinite over infinite, if it's just going to infinity, that's probably going to be an infinite discontinuity. Not going to happen. But if it's infinity over infinity, you have a hope. Okay? That's an indeterminate form. Okay? Here's another one. Infinity times 0. Who wins? Okay? This one's getting very, very big. That one's going to 0. Most of the time, anything times 0 is going to make it 0. But that's not, infinity isn't anything. So we don't know who's going to win that battle. So that's another one that may be that is an indeterminate form. And then one other, infinity minus infinity. Now infinity plus infinity, huge, okay? But infinity minus infinity, again, you don't know who wins. If this infinity is going up faster than that one, it's probably going to infinity. If this one's going up much faster than this one, then it's going to negative infinity. But if they're going about the same rate, that may have a limit, and they kind of cancel each other out. So these are your 4 indeterminate forms. This is the one you'll see most frequently. But if you have any of the others, those are also indeterminate forms, so you have to do something else. Okay? Okay. Indeterminate forms are warning signs that tell us more work needs to be done to evaluate the limit. Our strategy when that occurs, transform f of x algebraically like we did in the last example, if possible, into a new expression that it is defined and continuous at x equals c. Then evaluate the limit by substitution, plugging it in. Okay? So let's do this next example now. Unfortunately, they did way too much of it for us, but I'm going to clear this and we're going to start at the beginning. Okay? What the problem is, evaluate this limit. The limit as x approaches 3 of x squared minus 4x plus 13. Really? No, plus 3. Good. I was going to say you can't factor that one. Okay, plus 3. All right. Okay, good deal. Anyone else come in since I called roll? Okay, over 3, whoa, get my pen back, over, here it is here, x squared plus x minus 12. Okay, what would be your first line of approach? Plug it in, substitution. What would this give you? As x approaches 3, that's going to 9. Say again. Minus 12 would be 9 minus 12. Negative 3 plus 3, 0. Right now you know this is either going to have a limit of 0 or it's going to be indeterminate. Let's see what the denominator does for you. 0, indeterminate form. So what's our first line of an approach after you do substitution? And that didn't work. Factor, excellent. Now, I don't know how y'all factor. I'll give you my little thing. I unfoil it. That's what I call it. Never read a book that said that. But, when you're multiplying two binomials, you foil them, right? I'm going to unfoil it, but I don't quite spell it right. First, let's start with the first. What's the only possible factorization of x squared? X times x. Okay? Then, here's where we jump. We go and look at the sign of the last term. What is that? Plus. What does that tell you about these two signs? They've got to be the same. So then you look at the middle sign, and that's negative, so they both got to be negative. Okay? And then you try to think of some possible factorization for 3. What's the only possible factorization for 3? 3 and 1. Now you check it. That doesn't guarantee it factors. Check it. And you follow this. X times x, x squared, minus x, minus 3x, that's minus 4x, plus 3. Yes, that worked. Okay? Now, let's do the same with the denominator. Starting the same way. Only possible factorization for x squared, x times x. Then you look where? Sign of the last term is negative. What does that tell you about these two signs? Okay, they're different. One's positive, one's negative. Okay? Now, I want a factorization for 12 with one of the numbers being one more than the other, and it goes with which sign? The plus. 3 and 4 with 3 going with which sign? Yeah, the 3 is negative and the 4 is positive. Okay, again, always check and make sure it works. X times x, x squared, minus 3x plus 4x is plus x, and then 4 times minus 3 is minus 12. Fantastic, you've done it. What happens now? You can divide out the x minus 3's. Now, can you plug it in? Sure. Your substitution works here. What does that give you? 2 over 7. All right. Okay. This high-level math gets to you. Calculus is easy. They're adding, oh boy. Okay. All right. 2/7. The limit does exist. Even though it was a 0 over 0, the limit does exist. You can do the last part by substitution.
So what would happen if it didn't exist also?
If what?
If this didn't work?
If that didn't work? Okay, it depends on how it didn't work. Okay? If you came up with a negative 3 over 0, it's never gonna work. Okay? So hang that one up. If you came up with a 0 over 0, well, okay. Here's what you do next. You ask, you're going to get it. L'Hopital's rule. Does that answer anything for you? Okay. Have you heard of it? No. Okay. We'll get to that very shortly. Okay. That's what you do but it's a great question. If you get as far as you can and can't factor any further, you run out of ideas, and it's in one of these indeterminate forms, try L'Hopital's rule. and we'll get to that later, a nice little tool, okay? So nice, okay. So let's do another example. Any questions on this before I erase it? Okay, let's see if they have this next one. I think they do, yes. Okay, this is calculate the limit as x approaches pi halves of tangent x over secant x. And what would be your first attempt? Plug it in, plug it in. What is tangent of pi halves? Second? I mean, yeah, tangent of pi halves. What did you say? Yeah, it's going to infinity. From the left, it's going to infinity. From the right, to positive infinity. From the right, it's going. There it is, right there. There's tangent x, the blue line, going to infinity here, going to infinity there. Okay. How about secant x? It's also going to infinity. It's the red line here. Okay. Now they look different after it. The blue line, if they had continued doing, we do like this. It's really expanded the x scale and reduced. Because you see, there's pi halves, which is about 1.5. There's 1 on the y scale. I don't know why they did it this way, but they did. But the secant goes up like this. The tangent goes down like this. Okay, and both of them have another asymptote over at negative pi halves. And the tangent goes like this. The secant goes like this. They have another one at 3 halves pi. Okay, so this is an infinity over infinity. That's not an infinite discontinuity. It might look, if that's what you had, yeah, that would have been an infinite discontinuity. If that's what you had, the answer would be 0, okay, because 1 over infinity would be 0, approaching 0. But this is an infinity over infinity indeterminate form. So what might you try to do? How? Okay, let's factor that baby, okay? And tangent is, what were you saying? Sine x over cosine x. And secant is 1 over cosine x. And guess what? You can multiply numerator and denominator by cosine x, right? So you eliminate that, and what are you left with? Sine x. Can you take the limit of that as x approaches pi halves? Sure, what would that be? 1. Yes, they're both going to infinity, and it does appear they're going sort of right with each other. And if those two values, you might say, are staying so close to each other, they could be approaching 1. And sure enough, they are. Okay, does that make sense? Factoring worked there as well. Okay? Let's do example 3. Does anyone need that any longer? Oh, you do? Okay. Let me leave it there just a few minutes. Now, you see what I did. I just crossed them out, but really what you did was multiply numerator by cosine x and denominator by cosine x. Because what's cosine x over cosine x? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value, right? Okay. So that was a legal move. That wiped out this one and wiped out that one. Now, there's another part of me, but I'm going to suppress this part. It says, no, cosine x over cosine x when x is approaching 1/2, that would be 0 over 0. Can you multiply by indeterminate form? Well, we didn't get away with it, right? So it's all right. We did that before too, by the way. So, all right, got it? Let's see if they do. I don't think they have anything for example 3. No, that's example 5. So we'll go back and just do this one. All right. Example 3. Evaluate this one. The limit as x approaches 4 of the square root of x minus 2 over x minus 4. First approach. Plug it in, plug it in. What do you get here? As x approaches 4, that would be 2 minus 2 is 0 over 0, our good old 0 to 0 indeterminate form. Anyone want to try factoring that? Okay, I don't. Okay. Now, let me give you a hint. When you have a radical involved, and you can't think of anything else to do, I don't know if you remember back when you first studied radicals, especially if you had it in a denominator, what do we multiply by? The what? Okay, close. The conjugate. And is almost like an opposite. Now, this radical is in the denominator, but you do have a radical. You have an indeterminate form, so let's try that. Multiply by the radical's conjugate. And what would be the conjugate of that numerator? The square root of x plus 2. Now, you don't multiply by the conjugate of the denominator. No. You have to multiply by 1, right? You can do that anytime you want to. And 1 in this case is the square root of x plus 2, right? Square root of x plus 2 over square root of x plus 2 is 1. So you have to do the same thing to the numerator you do to the denominator. All right. Looks like it's going to mess up our denominator. We can live with that. What does it do to the numerator? Say again? And how does it do that? What does it become? Okay, I hear something, but I can't make it out. Okay, you get an x, good. Minus 4. Okay, and the denominator is x, don't multiply that, leave it alone, over the square root of x plus 2. Okay, and what happens there? Ha! The x minus 4's divide out, right? Leaving you 1 over the square root of x plus 2. Now, can you take a limit? What do you get? 1 over 4. Excellent. Okay? That's equal to 1 over 4. When you take the limit, I should be writing limit in there. I'm really lazy, so I'm not. You need, okay. Make sure you're remembering what you're doing. You're just messing with the inside, but you're still taking the limit. Plug in that. Does that make sense? Got it? Okay. Now this next one might seem like a bizarre thing to do, but in just a little while you'll see it's a very reasonable thing to do. Here is a limit. The limit, surprise, surprise, as h approaches 5, okay? Oh no, this isn't, I'm sorry, nothing special here. Of h, I just got fired up because I saw an h. It's just a letter. Square root of h plus 4 minus 3. Okay? First step, plug it in, plug it in. What does the numerator become? 0. Okay, denominator? 0, because 5 plus 4 is 9, square root of 9 is 3, 3 minus 3 is 0. So, based on what we did before, what might we try now? Say again? Okay. I'll let you factor that one. I'm not about to. Okay, let's multiply the conjugate. And which conjugate do you use? The denominator. And what would that be? the square root of h plus 4 plus 3, okay? And what would you have to do to the numerator? Same thing, multiply the square root of h plus 4 plus 3, because you got to multiply by 1, okay? You can do that anytime you want to, but nothing else, okay? Now, I'm going to leave that numerator alone, okay? H minus 5 times this ugly thing, the square root of h plus 4 plus 3. But let's mess with the denominator. And what does it become? H plus 4 minus 9. And what does that become? Second? H minus 5. And then what can we do? You see, plus 4 minus 9 is minus 5. Okay? Now what? Divide out the h minus 5s, and now what? Plug it in, and what do you get? Six. Very good. As h approaches 5, that would be 5 plus 4 is 9. Square root of 9 is 3. Plus 3 is 6. Good deal. So these indeterminate forms, even when they're really hairy looking, if you try to write tricks, usually you can get them to work. Okay. Now, the next one, I think, is this one that's on the board. Anyone? I'll leave this a little bit longer. Okay. Yes? Okay. This was when you multiply these two together, the radical times itself is just going to be what's under the radical, h plus 4, right? Minus the product of these. This is a sum times the difference of the same two numbers. That's the square of this minus the square of that, right? So the square of 3 is 9, so minus 9. So h plus 4 minus 9. Combine like terms, 4 minus 9 is minus 5, h minus 5. Does that answer what you were asking? Good deal. All right. The thing about when you have a radical in there, especially added to or subtracted from something, even if the second thing is also a radical, or the first thing's a number, the second thing's a radical. Whenever you have a radical involved with a sum or a difference, and you have an indeterminate form, try multiplying by the conjugate. Okay? May work, may not work, but that's usually our first thing. I can remember my calculus professor in college. We finished the calculus. We had quarter systems, so 5 quarters of calculus, and we finished everything we were supposed to do. I had an excellent instructor. I was so fortunate to have him all 5 terms, and so we actually finished a little early. He said, "Well, let me get you ready for differential equations," and so he started showing us a few things. He said, well, "Actually, with differential equations, what it is a number of tricks, and if you use a trick enough times and it works enough times, you call it a method." So that's the thing here. Here's a trick, try multiplying by the conjugate. If it works, call it a method, okay? So we'll call it a method. Okay, dumb illustration. Okay. Got it now? Let's clear this out of the way, and let's do example 5. They didn't write the limit for us, so let's write it down. Do the limit as x approaches 1 of 1 over x minus 1 minus 2 over x squared minus 1. Okay? And what might you try first? Plug it in. And what do you get? Okay, 1 over 0, which is an infinite form, minus 2 over 0, which is another infinite form. Okay? Now, since that's a minus sign in between, if that was a plus, hang it up. Never going to be anything but infinity. But this, because we don't know who's going to win here, or if either one of them wins, we need to try something. So if you look at that, and by the way, this is the, hold up. I'm sorry. Should have done this on the next slide. I thought I was on the next slide. Sorry about that. I'll show you the picture in a minute. What might you try here? Okay, now if that was an equal sign there, I certainly would agree with that. Yeah, I may still agree with it if I know what you mean by cross multiply. Kind of, but not quite. This is a subtraction of two fractional forms. How do you subtract fractions? You have to have a common denominator. So, in order to investigate the common denominator, what might we choose to do with especially that second denominator? Factor it. Very good. What would that factor as? X. Say again? Plus 1 times x minus 1. You see these conjugates, that's what you're using here too. They will come in really handy sometime, right? Now, can you see what the least common denominator between those two denominators would be? That second one, isn't it? So let's rewrite this way. We already had a 1 over x minus 1. Okay? And here we have a 2 over x plus 1 times x minus 1. But we need the same denominator. So what do we need to do to the first denominator to make it look like the second denominator? Multiply by x plus 1. But if you do that to the denominator, what had you better do? Multiply by the numerator as well. Okay? Now we have a subtraction that we can do, right? So let me write this. I'm taking a lot more steps here than I normally would. Okay? So this will be x plus 1 minus 2 over x minus 1 times x plus 1. Because you got the same denominator, just do your subtraction up top. What would you do next? Close your parentheses, of course. Okay. What would you do next? Say again? Simplify that numerator. What would that become? X minus 1. Right? And now what can you do? Wake up? No. Okay, what? Okay. Okay, divide out the x minus 1. And then what do we have? What can you do? Now we take our limit, and what do we get? 1/2. Nice, huh? Let's see if the book... Oh, yes, they got it too. That makes it even nicer. Okay? Now, what I forgot to do, I thought I had advanced to the next slide because they look similar. This was that slide. Okay? I'll blow it up for you since I've already done the... Oh, do I need to go back? Sorry. Took that off too soon. Anyone still need that? Everybody got it? Okay. Here was a picture. I thought I was on this picture. I just wasn't paying attention. Here's a picture that goes with that. Okay? The figure that goes with that is this one. Here's the blue is 1 over x minus 1, and you see that's got an infinite discontinuity. If that's all you had, there's no way you're going to get a solution. Okay? That would be infinite discontinuity, jump infinite discontinuity. No way you're going to get that if that's all you had. The red line, though, is this one, which is 2 over that. Plug in an x equal 1 there. If that's all you have, the limit just of that doesn't exist. The first limit doesn't exist. The bottom limit doesn't exist. They're both going to infinity. Infinite discontinuity with a jump to boot, okay? But what if you're subtracting those? Well, if you're subtracting them out here somewhere, you know, they give you some number. But what happens as you get closer and closer to 1? These are getting really close to each other, it looks like, as you get closer and closer to 1. Does it really have a subtraction there? And we found out there's no way graphically to show that. But, indeed, algebraically, you showed that it could happen. All right. Any questions on that? Should have had that slide up when I did the problem. I missed it. Okay, let's move on to example 6. Okay. What we want to do is take the limit of this one. The limit as x approaches 2 of x squared minus x plus 5 over x minus 2. First attack. Plug it in. And what do you get?
4, 2, 7.
4 minus 2. 2 plus, 7. You get 7. Ew. Said something wrong before, didn't I? Well, we'll see. Okay? Your denominator is a 0. So this is not an indeterminate form. This is 7 over 0, believe it or not. The one I was just making up before. It's 7 over 0. First inclination would be this doesn't have a limit. Okay? But let's see if we can do anything to see that. Okay? Now, no, it just doesn't have a limit. I mean, hang it up. There's just no reason to go any further. I thought what they were going to say is divide this into this. It's still not going to have a limit. When you have an undefined form like that, something not 0 over 0, it's never going to have a limit. And there's nothing you can do to this to make it have one. You can't factor that numerator. I mean, even if you did, it probably isn't going to work. But that's not even factorable, okay? Yeah. So, nothing you can do. If it gives you an undefined form, this happens to be 7 over 0, stop right there. It has no limit, okay? All right, so it's infinite but not indeterminate. Okay. In other words, undefined but not indeterminate. All right. I don't think example 7 has a slide, so let's do example 7 here. Okay. Calculate this. Here is where we're getting to something we're going to get to later. The limit, I saw the h's before and thought we were there. We're not yet. Now we are. As h approaches 0 of h minus a squared minus a squared over h. Not too many numbers in this one, are there? Okay? But you can still do it. Let's see what happens. Plug it in, and what do you get here? Okay, in the numerator you get a 0, in the denominator you get a 0. Okay, so that is an indeterminate form. Okay, let's see if we can do it. Now everybody sees why that's indeterminate. If h approaches 0, that goes to negative a. But negative a squared is positive a squared, minus a squared is 0, and that's 0. Okay. So what might you choose to do? None of our other tricks are going to work here, but what might you choose to do? Okay, yeah, let's expand that binomial square, okay? Does anyone know what that would be? And he said pull it out, take it over to the side and write it out. That's perfectly fine. Or, okay, what do you say? H squared plus 2, only it's a minus 2AH, isn't it? Because that minus sign in there, okay? Minus 2AH. Continue. I interrupted you. Plus A squared minus A squared over H, right? Everybody agree with that? If you don't know how to expand a binomial squared, it's the first one squared, twice the product, and the last one squared. So H squared minus 2AH plus A squared, because minus times minus is plus. Okay, what would you do next? Okay, and if you don't remember that, write it over on the side. H minus A times H minus A and what? And you'll see you'll get the same result. Okay? What do you do next? Oh, yeah. A squared, combine like terms, A squared minus A squared is 0. Okay? Now what might you try to do? Factor out an H in the numerator. Because all you have left is H squared minus 2AH. You can factor out an H. And what are you left with? H minus 2A. And then divide by H. But now what can you do? Divide out an H. And now what might you try? Say again? Now you plug it in. Take the limit now, and what do you get? Negative 2A. Whatever that A is, you have an answer. Okay? And sure enough, that's what you do. So you can do it even if you really have a shortage of numbers. You can still take limits. Sometimes. Okay? Get used to that. You're going to see something like that pretty frequently at the beginning of the next chapter. All right. Except I wrote the problem wrong, didn't I? It was H plus A. And this should have been the plus. And then this would have been a plus, and that would have been a plus. I wrote the problem wrong. Sorry. I don't know where my eyes were. Okay. I guess I was seeing the second minus. It was H plus A squared. We did it right for that one. This is right for this one. H plus A minus A. Sorry about that. Still came out right. And that's it for section 2.5. The summary's there. Repeats the 4 types of indeterminate forms that we have. 0 over 0 we're most familiar with. Infinity over infinity comes up occasionally. 0 times infinity. We actually didn't do one with that, an example with that. I bet you they'll find some in the book for you, though. And then infinity minus infinity, we did do one of those, too. Want to do the preliminary questions? I know you do, don't you? Well, we don't have to do them if you don't want to. Do you find them useful? Give me a yes or a no. Y'all have no opinion this morning, do you? Okay. You like doing these or not? Do you find them useful? Huh?
It's the morning.
Oh, look, you were here super early. You got plenty of time to wake up.
I was
Okay.
here because my dad works at the courthouse.
I see. Not by choice, by demand, huh? Okay. Do y'all find these helpful or not? Preliminary questions. Huh? Okay, let's do number 1. Which of the following is indeterminate at x equal 1? I'm stuck. Sorry. Okay. All right. X squared plus 1 over x minus 1. Is that indeterminate at x equal 1? No. That would be 2 over 0, which is undefined. Don't even try to find that. That's going to be a infinite discontinuity. It's not going to have a limit. Okay? How about the second one? X squared minus 1 over x plus 2. Is that indeterminate at x equal 1? It'd be 0 over 3. Guess what that is? 0. It has a limit. The limit's 0. Done. No, it doesn't have, it's not indeterminate. That is a number 0. Okay? You can always have a 0 in the denominator. It's just you can't have one in the in the numerator. You can't have one in the denominator. If you have a 0 in the denominator and anything other than a 0 in the numerator, I said it right. A 0 in the numerator and anything other than a 0 in the denominator, that answer is 0. Okay? It has a limit. The limit's 0. Okay? But it's when you have a 0 in the denominator. If you have anything else upstairs that's not 0, no limit exists. But if you have a 0 over 0, that's your indeterminate. That is determined, and that is 0. Not indeterminate, not undefined, that's 0. Okay, how about this one? X squared minus 1 over the square root of x plus 3 minus 2. What's that? That would be what? So that would be an indeterminate form. You're absolutely right. Okay, let's look at the fourth one. X squared plus 1. Can I stop right there? Yeah, I could. Because that never is going to be 0 at x equal 1. In fact, it's never, ever, 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 ever going to be 0. You can't have a 0 there. So let's just write the rest of it. The square root of x plus 3 minus 2. That would be what? 2 over 0. And what kind of form is that? That's an undefined form. It's an infinite discontinuity. You're never going to have a limit with that. Something over 0, never going to have a limit. Unless that something is 0, and then it may. 0 over 0, that's indeterminate. You have to investigate further. 0 over something, yeah, that's going to be 0. You don't have to investigate any further. That will be 0. Unless that something is a 0, 0, 0, then you have to investigate further. And that's the same as that. Okay. Helpful or not? Okay. You want to do any of the rest of them or go on? Go on. Okay. All right. Homework exercises then are either 1 or 3, or both if you choose. Any of the odds 5 through 33. There's a whole passel of those, maybe even a passel and a half of them. Okay. Now, 35 says you need a graphing utility. If you can do it without a graphing utility, do it. I think maybe you can, but I haven't worked it out fully, so I'm not sure. But if you get stuck, don't worry with it, unless you have a graphing utility. Okay? Then do any of the odds 37 to 41. Do 43. And then do any of the odds 45 through 53. All right? And if you find all of those way too easy, you can try some of the others if you'd like. 55 through, or 57, 59. But you're not required to do those. All right. Good deal. Any questions? Okay? That is the end of 2.5. Let's move on to 2.6. Again, PowerPoint takes way too long. But at least it went through the slides nicely. It's just loading it is the pain in the neck. All right, it's open. Let's get the slideshow. Okay, I know this is a really long class. I know we did get started a little late, but if anyone does need to take a break, I call them bladder breaks, but you can do any kind of break you want. If you do need one, just let me know. We can take a very short break if anyone needs it. If y'all don't, at some point I might, so we're going to have one anyway. But if you need one, don't sit and suffer. Let's go. All right, now let's consider trigonometric limits. Actually, we already did one. Remember the tangent over secant? Yeah, we did that. In our study of the derivative, which we haven't gotten to yet, we will need to evaluate certain limits involving transcendental functions such as sines and cosines. Excuse me. The algebraic techniques of the previous section are often ineffective for such functions. We did some before that did work. And other tools are required. In this section, we discuss one such tool, and this is the squeeze theorem. Now, these math books love this. In reality, yeah, I guess you use it sometimes, but usually it's pretty obvious when you can or can't. And if it's not, it can be sort of a pain. So here's an example, not of anything specific, just three functions here. Okay? Here's your function of interest, and that's your f of x. Happens to have a discontinuity at c. So we don't know what's happening there. Okay? Now, there is also another function, u of x, which is always greater than or equal to, you don't see it equal to, f of x. There's another function down here, L of x, think upper, lower, okay, L of x, which is always less than or maybe possibly equal to f of x everywhere, at least on the domain you're interested in. Now, if you're guaranteed that u of x is always greater than or equal to f of x, and L of x is always less than or equal to f of x, then, even though f of x may not be defined there, you might know that the value here has to be between this value and that. But in this case, it doesn't tell you very much. You just know it's probably going to be between this number and that number, okay? That doesn't tell you a lot, okay? F is trapped between the upper and lower and upper, but it's not squeezed, so it doesn't tell you anything. Now, what if you had a circumstance like this? That upper function, okay, now let's state again now. F of x is the only one with the discontinuity here. Your upper function, which is always greater than or could be equal to f of x, does not have a discontinuity there, and the lower function doesn't either. But look what? Those with upper being always greater than or equal to f of x, the lower always less than or equal to f of x, if indeed they meet at x equals c and they're squeezed, that means f has to have a limit there. Well, guess what? Just looking at left and right limits, that tells you it's got to have a limit there. But if you can do this when sometimes it's not really clear whether they're what your left and right limits are, the squeeze theorem can give it to you. Okay? Again, I don't find lots of use for it, but you see that's got to be the case. If u of x is always greater than or equal to f of x, and L of x is always less than or equal to f of x, and they both have limits as x approaches c, and they have the same limit, then f of x has to have that same limit. Okay? So that leads to the squeeze theorem. Basically, I've just said all this, but here it is written out in math speak. Okay, and since we all love to speak in math speak, let's get it written that way. Assume that for x not equal to c on some open interval containing c. So you've got functions going along here, and we're not talking about x equals c, but you're an interval that contains c. Okay? Now, if on some open interval, this L of x is always less than or equal to f of x, and the f of x is always less than or equal to u of x. In other words, they never cross. They can touch, but they don't cross. Okay? Then, and this is true, that limit of the lower function as x approaches c exists, and the limit of the upper function as x approaches c exists, and those two limits are the same, and since f is in between those everywhere else, it's in between them there too, and if they have the same limit there, then f of x, the limit as x approaches c, even though it may not be defined there, that does exist, and the limit as x approaches c of f of x is that same limit that is there. Okay? Now, this is the same as left and right hand limits, basically. I mean, so what's the big news here? I don't know. Okay? But they like squeeze theorem. Okay? Now, here is example 1. Get my pen readjusted. Okay. The limit as x approaches 0 of x times the sine of 1 over x, okay, they want to show that's equal to 0. Okay. Now, they're almost wanting me to use some words here. Okay. This is an indeterminate form. Not an indeterminate. This is an undefined form. That limit does not exist. Now, the sign of that is confined between plus or minus 1. Okay? Even though this goes to an infinity, the sine function stays between plus or minus 1 all the way to infinity every time. Okay? It always stays between plus or minus 1. So, this thing is bounded. This is not. This is. Okay? That's the function we're dealing with. Now we have a product of 0 times a function that is not defined. Okay? Sine of 1 over x is just not ever defined. I mean, it does, well, it's defined, but it doesn't have a limit. Okay? But it's bounded between plus or minus 1. And when you multiply 0 times anything, now 0 times infinity, we don't know what's going to happen there. It's just not clear. Okay? But 0 times a number, especially a number that's bounded by plus or minus 1, that usually winds up being 0. But there's no way to prove that. I mean, you can't plug it in. That's not going to work. Okay? So here's what we do. Okay? Because, like I just said, sine of 1 over x is always between plus or minus 1. Does everybody buy that? Sine is always between plus or minus 1. Always, no matter what number you put there, how big the number gets, sine stays between plus or minus 1. Okay? Okay? Now, there's one way I would like to do the problem, but I want to do it the way the book does. Okay? the limit as x approaches 0 of sine 1 over x doesn't exist, does not exist. But we know this is true, okay? Now, what we're going to do here is kind of a trick, okay? And here's the trick, okay? Let's multiply all three sides of that inequality by the absolute value of x. So minus the absolute value of x is less than or equal to the absolute value of x times sine of 1 over x, and that's less than or equal to absolute value of x. Would you buy that? Okay? Because absolute value of x is some number. Okay, you can multiply by same thing by all three sides. Okay? Now, the reason you have to use absolute value of x, if x were negative, then that multiplying by a negative number flips the inequality. So you get a little messy there. But by multiplying by something that's guaranteed not to be negative, that's what it gives you. Okay. Now, what we're going to do next doesn't quite seem fair, but it is. This piecewise defined function here. Oh, by the way, there's y is equal to absolute value of x. Oh, I'm sorry. This is y is equal to absolute value of x. This is y is equal to minus absolute value of x. Okay? And we see that this is always less than or equal to that product. Okay, because that product is the same. Okay? And this one's always greater than that. This tells you that. So therefore, what's in here has to be there. Well, the limit of this is x approaches 0 is 0. The limit of that is x approaches 0 is 0. So this limit also has to be 0. That's the squeeze. This is always less than or equal to that. This is always this is the function you had to begin with, without the absolute value bars in there. Okay? Now, sorry about that, but really it seemed like you had to put on that. The book didn't, and they didn't rationalize why they didn't. Okay? But it's okay. If this is always positive. If x were allowed as x gets close to 0 to be negative, all it does is go down here. Basically what this is doing is taking out this part. If you flip it around and did minus absolute value of x, you'd have the same thing, and that would take into account this. So this one doesn't both. And since it's always less than the absolute value of x, less than or equal to, several places is equal to it, like here and 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 here. There's several places it's equal to, but it's always in between those two. And since this has a limit as x approaches 0, that has a limit, this one has to too. That's the squeeze there. All right. Now, way back in 2.2, I don't know if you remember, we found numerical and graphical evidence that these two things were true. I don't know if you recall it or not, but we did. Okay? We set up tables and took the quotient of sine theta over theta, and we let that get closer and closer to 0 from the left and from the right, and it came to 1. We drew it on a graph, and it wasn't defined to x equals 0, but it approached that. And the same thing with 1 minus cosine. So these are two very important trigonometric limits. Sine of theta over theta, limit of that as x approaches 0 is 1. that's an indeterminate form, and we did it numerically and graphically, it's just really hard to prove algebraically, okay? And we also did that one numerically and graphically, and that's hard to prove algebraic. But once you have these done, then that opens up a whole new way to do your sine and cosine. These are the linchpins, okay? And basically, well, okay. So know those. Here was the graphical picture. Whoa. See. Don't tell me they don't show it. Yuck. Okay. In your text, at least in the new edition, they show the graph of both of those. Well, not quite. They show y is equal to sine theta over theta. That's the red line in your text. And that's going to 1 as x approaches 0. Okay, as theta approaches 0. All right. Now they show y is equal to 1, and they show y is equal to cosine theta, okay? And as the difference of those would be 0, okay? Because as theta approaches 0, the difference between those two is 0. So they do show the graphical illustration that corresponds to both of those. Okay. Now, let's do theorem 3. We're not going to do it, but I'm going to show it to you. Okay. Actually, it's from that graph. If you look at that graph, cosine theta, which is the blue graph in your text, you see is always less than or equal to the sine theta over theta, the red graph. The green graph, y is equal to 1, is also always greater than or equal to sine theta over theta. You can see it's always greater. Okay? Now, according to the graph, this is true, and as theta approaches 0 here, that's approaching 1. As theta approaches 0, 1 is still 1, so this has to be 1. So there's another illustration of this, that this has to be, this is approaching 1. Now, this is true for all thetas between minus pi halves and pi halves. You could expand that some if you wanted to, in fact, as far as you'd like. Now, theta can't be 0 because of this, but as it approaches 0, it goes between these two. This has a limit of 1, that has a limit of 1, so this has a limit of 1. So what we did earlier, graphically and numerically, now we've used the squeeze theorem to show, yeah, it's got to be true. But again, we use the graphs to show it between that. Okay. You see, we could have done from minus pi to pi, but we couldn't go much beyond that because you see, I wish they had the figure here. You see the cosine function at some point does this and goes above, and it actually, then this is not always true. But between minus pi and pi, this is true. After a while, cosine gets bigger than this, so you can't do that anymore. But on the interval that contains 0, as long as you can limit it there and it's always true, it's fine. Now, they do have a proof here. Are any of you actually math majors? Okay, most of you are pre-engineering or something like that. Okay, I hate to say this way. Most of the time, engineers really don't care that much about the math proofs. They just want something that works, right? Okay, so if you were a math major, I would say by all means follow this, and if you have any questions, we'll go through it. But I just don't want to take a huge amount of time to do that. It's a pretty interesting proof, especially since they use some graphics in there too. So part of this is from that. They don't show the figure. I don't think they do. No, they don't. But if you got your text there open, or you're looking at it somewhere there, you'll see the figure 5, at least in the new book. They show a triangle inside of a circle. That's the triangle OAB, where O is the origin, the center of the circle, and A and B are 2 points. A is on the x-axis and B is somewhere in the first quadrant. Triangle inside that. Okay? Then the area of the sector that is the sector of the circle, that happens to be 1/2 theta, okay? And they show it's larger than the first one. And then they show the triangle that circumscribes that circle has some outside. So obviously that triangle is greater than the area of the sector, okay? So this is true then. OAC, you have to have the picture for this to make sense. But it's a pretty interesting way to prove this. And when you do that, you come down to this, and you have to have those triangles and circles there. This would be the area of OAB, 1/2 sine theta. Oh, sine theta, yeah. You can see that's true. This is the area of the sector already given, and this is the area of the tangent theta, which is sine over cosine, okay? And this is always less than or equal to that, less than or equal to that. This is the triangle inside the sector, that's the triangle outside the sector. The area of the sector is in between the two, okay? I'm not doing the whole proof for you, but that's those two combined. And you wind up with that if you divide both the left-hand side of this by theta, then you have 1/2 sine theta over theta is less than or equal to 1/2, okay? Or you can multiply both sides by 2. Sine theta over theta is less than or equal to 1. And that's what they get here, okay? I can blow it up for you if that makes it easier to see. I know that's ridiculously small to do that little thing in a whole slide. That's as far as I can blow it, sorry. Okay? Now, using the other side, okay, let's go back to, to this. We use the right 2 here. If you use the left 2, if you use the right 2, multiply both sides by 2, which I think we should have done anyway. And multiply both sides by cosine theta, you get cosine theta is less than or equal to sine theta over theta. I think that's what they do next. Yeah. That gives you this one. Okay? So then you have your squeeze theorem in place then, because you have this side here, and on the other side you have this is less than or equal to 1 from the previous slide. That one, okay? So therefore you have it not, okay? And you have the graphs of all those, okay? Look at that. Here they are. They just have the slides out of order. Okay. There's this graph I was looking for, figure 4. Sorry, I don't know why they had it so squirrely. This was, blow this up. This shows the squeeze theorem right here. Okay. In between, now you see this keeps coming down here, this one goes up here. So you can't get out here, because then cosine theta may actually be a greater. Anywhere between minus pi and pi, they said between minus pi halves and pi halves, fine. Anywhere in here, the blue line is always less than or equal to the red line is always less than or equal to the green line. Okay? Pretty obvious from the graph. This is the cosine function. This is sine theta over theta. Someone had the graph for you, and there's y is equal to 1. So cosine is less than or equal to sine theta over theta is less than or equal to 1. As theta approaches 0, this goes to 1, that goes to 1, and since that's in between, it has to go to 1 too. So there's graphically the squeeze theorem. Okay. Here were those triangles I was describing to you before, trying to wave my arms about. Let's blow these up too. I wasn't going to do this because I had forgotten these were on the slide set. Okay. This is the triangle that's circumscribed by a given circle. This is a unit circle, by the way. Okay? So, what is the area of this triangle? 1/2 the base, which is 1, times the height of this triangle here, OAB. Okay? Well, the height there is the sine of theta, because sine of theta is opposite over adjacent. Opposite over hypotenuse. The hypotenuse is 1, because this is a unit circle. So multiply both sides of the equation by 1, and you get sine theta is equal to, this side is sine theta. Okay? The height is sine theta. So 1/2 the base times the height is 1/2 sine theta. That's the area of that triangle that's circumscribed by that circle, but inscribed in the circle. Here is the sector. Okay, now I don't know if you remember the equation for the area of a section. Okay. All right. We should have probably taken a break, didn't you? I didn't realize you took a break. You could have all taken one. We will in just a second. Okay? Area of a sector is 1/2 r theta. You can go back to your trig and remember that. But what's the radius of a unit circle? 1. So the area of that sector is 1/2 theta. Theta measured in radians. This equation, this formula does not work for theta in degrees. This must be in radians. Why? Because the definition of a radian is the ratio of the arc length to the radius. Okay? That's where this comes from. So you've got to have the theta in radians here. They didn't, I don't know if they mentioned that. It has to be in radians. And since you're using radians there, use them everywhere. Okay, this one out here, this triangle has a radius of 1, a base of 1. Its height is here. That's the right triangle on the outside. And let's see, how can we do that? Well, what is the tangent of this angle would be opposite over adjacent. The adjacent is 1. So the height here is the opposite, which is tan theta. Opposite is equal to tan theta. So this opposite side is tan theta. So the area of this triangle is 1/2 tan theta. This is 1/2 sine theta, and this is 1/2 theta. Okay? Now, set those up. This is always less than or equal to this, is less than or equal to that, and that's where they went. Proceeded to get the other things. Using these two, wipe out the 1/2, divide by this, and you have sine theta over theta is less than or equal to 1. Using these two, multiply by 2, and you get sine theta over cosine theta. Okay? And that then divide by theta, multiply by cosine theta, and you have cosine theta, is that right, is less than or equal to sine theta over theta. Okay. So that's what we were doing before. Okay. Now, this is example 2. I'm not going to do any more on the proof. If you want to carry the proof on out, just keep looking. We basically did it all. We just didn't fill in all the gaps. I talked them in, but I didn't write them in. Let's move to example 2. Let's investigate this. The limit as h approaches 0 of sine of 4h over h. Wait a minute, folks. I know what sine h over h is. The limit as h approaches 0. That's 1. I don't know what it is for sine 4h over h. Do you? Haven't had that. Okay. What if that was sine 4h over 4h? I know that one. That's 1, right? So here's the trick. Multiply the denominator by 4 and the numerator by 4. Okay? Now remember one of the limits laws? The limit of a constant times a function is the constant times the limit. So this would be the same as 4 times the limit as h approaches 0 of sine 4h over 4h. And guess what that would be? You do it. Huh? Okay, wait, okay. This is an indeterminate form, but this, how about doing this? For limit as theta approaches 0, let's do let theta equal 4h. Is that a legal substitution? As h is going to 0, theta is going to 0, right? Okay, and then you'd have sine theta over theta. We know what that is, don't we? 1. All that we did before showed that was 1, so this is equal to 4. 4 times 1 is 1. Okay? Now, they did it the long way, numerically. They plug in a plus or minus, they plug in a 1 for h on the original thing there, before I multiply by 4. Okay? So let's wipe this out. Before I multiplied by 4. Okay? That was the original problem. Okay? And they plugged in a 1. Now you're in radians. Be sure you're in radians. Okay? And you do sine of 4 over 4, and you get a negative number. Well, that's pretty far away from 0. So do a plus or minus 0.5, and you get a 1.8. Well, you're still pretty far from 0. 0.2, 3.5, 0.1, 3.8, 0.05, 3.9, 0.01, 3.99, 0.005, 3.999, you know, yeah, that's getting close to 4. But see, algebraically, you could get there in just a couple steps without having to do all the math. Because not only did you have to plug the pluses in, you had to plug the minuses in too. But guess what? As long as your h is closer enough to 0, if you have a minus, that's why all these turn out positive. This one doesn't. Because sine is negative here, and x is negative here, so, or h is negative here. So as long as you're inside that, then this is a negative over a negative. For negatives, positive over positive, so they all wind up being positive once you get close enough in. Okay. I don't know if that made any sense or not. Okay. but that has a limit of 4. Okay. Before we attack number 3, I've got to have a bladder break. I thought maybe I could make it. I can't. So let's take a very quick, keep it less than 5 minutes, as much less than 5 minutes as you can. Okay. So again, problems such as the one we just did, that was example 2. Boy, algebraic approach to me is a lot simpler than doing a numerical approach, though they confirm each other. I think, no. Oh, this shows what we just did, okay? I'm not apologetic that I did it because I'd rather you think through it rather than just read it. If you actually do it, it's more active than just reading about it. So here we had the limit of this. Now that's not a form we know a limit to, but it would be if you had a 4 down here. So, yeah, well they did it all in one step without showing you the step. They multiply this by 4 and that by 4. There's the 4 up top, and then they changed the 4h to theta, just like I did. And then that should be 4 times theta over sine theta over theta. Bring the 4 on the outside. We know the limit of this from earlier is 1. So it's 4 times 1. Okay. Or you can do it by the table. This is easier. Okay? Now, that's the last slide here, but there is another example. Find this limit. The limit as x approaches 0 of tangent of 3x over tangent of 2x. Okay. Now, a little more complicated here, isn't it? Let's stop and just sort of think about this. The first thing you try is substitution. What do you get? Tangent of 0 is? No, 0. Tangent of pi halves is infinity. Tangent of 0 is 0. See it? Just like this, 0. And tangent of 0 is 0. So it's an indeterminate form. Okay? Now, I don't know any quick and easy limit things with tangents. I do know with sines and cosines. The cosines are a little more complicated. So let's now write this as, now I'm not writing the limit. You really should, but just to save space, I don't. Make this as sine of, that's an ugly sign, of 3x over cosine of 3x. Now I'm doing this for a reason. And this one would be sine of 2x over cosine of 2x. Now that's a little bit of a strange way to do it, wouldn't you say? Okay. Now, yeah, that's what they did too. No, they didn't. I thought they were going to do it this way. Let me go back and make it more reasonable. I thought they were going to do it this way, but let's start over. Okay. Sine of 3x over cosine 3x over sine 2x over cosine 2x, but if you bring that up here, that would be cosine 2x over sine 2x. Okay. Do you see that as a legal move? When you have it in the denominator, you flip it and bring it up. You know, that gives you. If you divide by fractional form, you invert and multiply. So that gives you that. Okay? Now, they started off this way. Now they rearrange them, and that's what I did. I thought they were going to wind up doing that, but I just did it in one step. let's get the signs together and the okay, no, I'm sorry. Trying to follow the same device the book does. Okay. Now, what they're going to do next is this very thing they've got here, multiply it by x over x. Is that legal? Yeah, x over x is 1. Except, of course, if x is getting close to 0. But as long as x is not 0, which is a limit, it never is, has to be actually 0, that's still a legal thing to do. Okay. Now what we do, okay, is this. We rearrange this one and put this numerator over that denominator. Okay? So that'll be sine 3x over x. Let's put this denominator under that numerator, x over sine 2x. That's legal, right? And then we'll leave alone cosine 2x over cosine 3x. Leave those alone, okay? Now, doing what we did before, multiplying this by 3 and that by 3, right? Multiplying this one by 2 and this by 2, what's the limit of this? Right there. Limit of sine theta over theta is 1, right? Now, let me also do this. Sine of theta over sine theta would also be 1, right? It's still 1, okay? So, nope, this one, okay? This becomes 1. This becomes 1. Okay, so now we have the limit of 3 over 2, this 3 and that 2, times cosine 2x over cosine 3x. Now take the limit of that as x approaches 0. Well, 3 halves is 3 halves, right? What is, as x approaches 0, 2x is approaching 0. What's cosine of 0? Cosine of 0? 1. Cosine of, as x approaches 0, 3x approaches 0, cosine of 0 is 1. So this is just 1 over 1. So our answer is 3 halves. Do you see that? A little tricky, but certainly doable. All right. So that finishes 2.6. How about these preliminary questions? You want to do any of those or not? None? Okay. Homework exercises here. Do number 1, or I'd say do any of the odds 1 through 5. Okay. You may want to do more than 1 because they're not all the same, but you might want to do at least one of those. Then do any of the odds 7 through 15. Okay. Then do any of the odds 17 through 25. All right. 27 is very similar to one we did in class. In fact, a couple we did in class, so I think you can do that pretty easily. Okay. And then do any of the odds 29 through 47. Okay. Then take a look at the odds 49 through either 49 or 51 or both. They're dissimilar problems, so you may want to do both, but at least do one of those. Try them anyway. Then do either 53 or 55. Those are more similar. And then if you really get a hankering to do more, you can look at 57 or 59, but I don't require those. Okay. All right, that finishes 2.6. Any questions on 2.6? Okay. Lots of homework here, folks. Now, I don't take up homework, but I want you to do it because guess what? When you get the test, they're going to be problems a lot like your homework exercises was. If you haven't practiced on those as we've been doing them, when you get the test, it's going to be almost overwhelming. So I would definitely be doing these as you go. Okay? It's up to you. You can either wait and be overwhelmed, or you can do a little bit at a time and just take it in stride. I'd say take it in stride. Now, if you're having trouble finding answers for any of them, of course, I give you odd numbers answers in the book, but if you don't see how they got those answers, you can bring those to me and we'll go over those. You can ask them in class. I'll be glad to work any homework exercise in class. Okay? Even those that aren't homework exercises, you can ask those too. Okay. But we've moved so fast in the summertime, we've just gone through two pretty major problem sets. Please don't ignore them. Okay. Let's move on to 2.7. Okay. Wait a minute. That looks just like 2.6. I think I hit the wrong one. Yep. Yeah. Okay. Either my cursor was in the wrong place or something, but I went to the wrong section. 2.7. And we got to wait for this. I'm going to pause for just a moment here and look up something. All right. 2.7 is limits at infinity, which almost by definition it almost sounds like a contradiction in terms. Okay? Some of this is certainly stuff you need, but others of it is really stretching really what we really mean by limits. So let's what I'm getting at is in this section, I'm going to go over it with you, but I'm not actually going to test you on much of anything in here because, let me see, this up just a little bit. Almost by definition, the limit at infinity, where is infinity? But here is the Earth's average temperature according to a simple climate model in response to a 0.25% increase in solar radiation. If for some reason the sun started radiating more, or we got a little closer to the sun, what would that do to our temperature? Okay? And this is what the model shows. If we were, I'm only assuming here that we started having average temperature of 283 K. Now notice we don't say degrees when we're dealing with Kelvin. Okay? It's 283 K. Okay? Stuck in my hair. What that was. Okay. Okay. 283. If that's what it was, and then we had a 0.25%. That sounds pretty small. Increase in solar radiation. What would our average temperature go to? This shows that it would take a while, years in fact, but it would approach, maybe never quite get to, but really approach a limit at infinity of going up 0.25 K. which seems a little bizarre. That would be exactly the same amount. But according to that model, it would go up to 283.225, 255. Yeah, okay, it's a little bit more, 0.255K. Now that's a model. You know, things don't always follow models, but if everything we've seen in the past follows the model well, then this would be a projection in the future. Okay, so that is in a sense a limit at infinity. Okay, and that sort of does make sense, even though you're going to an infinity. That is, the t is going to infinity. Okay, and that would happen anytime you have, and what you call this is a horizontal asymptote. And sometimes studying the model, you could tell what that horizontal asymptote was, and you wouldn't actually have to calculate a limit. But the graph shows it does appear to have a limit there. Now, that's one of the few examples I can really think of that makes sense for evaluating limits at infinity. So basically, I'm just going to do a slideshow of this, and probably not take that long per slide, but just show you these slides. Here's another situation. And they don't give you the function. It's some weird, wacky kind of function, but it has a limit as the x goes to negative infinity, then this is approaching 3. As x goes to positive infinity, as x goes to the limit of your function, would be 7. Now, I can't even imagine what kind of function would do this. Now notice in between, it can do all sorts of things. It can go less than 3. It can go way more than 7. It can do all sorts of things, but the limit as x approaches infinity to negative infinity or positive infinity, there are limits here. Okay? Now, are there ways to find those without drawing graphs? Yeah, there are. You know, if you have a function. I would hate to see what that function looks like, because that is one weird function. But you could do that. Okay? And we'll get there a little later. Okay? Now, there are other types of functions that don't have limits as you go to infinity. Some of these are very familiar to us. The exponential function. There is a limit as x goes to negative infinity. What's that? 0. The closer you get to negative infinity, the closer and closer that goes to 0. Never gets to 0, but it approaches that as a horizontal asymptote. But what happens as x goes to positive infinity? The function goes to positive infinity. There is no limit. Plus infinity is not a number, so it cannot be a limit. People treat it as if it's a number sometimes, but it's not. That has no limit. This has a limit, 0. That's a number, a real number. That one, as x goes to positive infinity, the function is going to positive infinity even faster. Okay? Here's another kind of function, sine function, or cosine, either one of the two. Okay, you can tell this is sine, because it's 0, 0, equals something down from there. Does that have a limit as x goes to infinity? No, it just constantly goes between plus or minus 1, plus or minus 1, plus or minus 1. That's why that function 1 over x makes no sense, sine of 1 over x. And as x goes to negative infinity, this has no limit. This one has a limit as x goes to negative infinity, not as it goes to positive, because that's unbounded. It goes to infinity even faster. This one, however, is bounded both above and below, but it never approaches either one of those. It just keeps going back and forth as long as you keep putting more values in. So this has no limit at all, positive infinity or negative infinity. Okay? Now, here's a theorem, and again, I think it's most of these things are either common sense or They don't make any sense, okay? In neither case do you need to worry with them. For all n greater than 0, in other words, positive n's here, okay? The limit as x approaches infinity of x raised to some positive exponent, that's going to be infinity. Now, even if that positive exponent is 0.00001, but if x is going to infinity, that is the 1,000th root of infinity, is still an infinitely large number. Now, this is where this is not a number, so to me, the limit doesn't exist. I don't like writing it as this because that indicates, or that at least on some level says to me there is a limit, it's infinity. No, infinity is not a limit. It's going infinitely large. So this is saying it has no limit. Okay. But, now for n being positive, if you have x going to, as x goes to infinity, of 1 over x to the n. If x to the n is getting infinitely large, 1 over x to the n is going to 0. Because the larger your number is in the denominator, the closer you're getting to 0. Okay? So this does have a limit. Even as x goes to infinity, that limit exists at 0. Okay? So to me, this has no limit, limit is at 0. And frankly, you've already been doing this before. If you remember back when you did rational functions and you did the leading coefficient, ratio of leading coefficients for horizontal asymptotes, you did this. You were doing it then. Okay. If n is a whole number, okay, a whole number, that means 0, 1, 2, 3, 4, 5. No negatives, only whole numbers. As x goes to negative infinity, okay, x to the n, as x is a negative number, okay, and going to any negative number, and large negative numbers, and n is an even whole number, 0, 2, 4, 6, 8, 10, 12, this thing is going to positive infinity. In other words, you're raising it to a large number. Now, I said that wrong. X to the 0th would be 1. So that doesn't fit here. But any n, oh yeah, this is still n greater than 0. Sorry about that. N is a whole number greater than 0. They should have said a natural accounting number here. Okay. Greater than 0. You don't count 0. Then this goes to positive infinity. But if x is going to negative infinity, so in other words, a large negative number raised to a negative exponent, an odd exponent is going to be a large negative number. Okay? But again, those are infinities, the limits don't exist. Okay? But whether n is even or odd, when your x is going to negative infinity, and this is 1 over x to the n, this is going to 0. It's either going to 0 from the top or going to 0, I'm sorry. Going to 0 from the top or going to 0 from the bottom, but it's still going to 0. So this goes to 0, whether x, for a power function, 1 over a power function, is always going to go to 0, whether n is x is going to positive infinity or negative infinity. Always approaching 0. And if x is going to positive infinity, x to the n, is the limit doesn't exist. Okay, positively or negatively, it doesn't exist. So again, these are sort of Weasley type things, but they're all true. But why say the limit is infinity? That means there is no limit. So why call it? Write it as if it is. Okay. I can't get all 3 of these on, so let's get 2 of them. Okay. This shows that second thing, the one that was down here before. As long as n is even, x at an even power is going to be positive this way for positive x's, but for negative x's, as long as the n is positive, it's going to be positive. This is y is equal to n squared, x squared. This is y is equal to x to the fourth. Notice it's steeper here, flatter near 0. X to the 6th would be even steeper here, flatter here, steeper there. The 8 to the 18th to the 22nd, you know, it just get flatter down here, steeper here, but as x approaches positive infinity, positive infinity, negative infinity, positive infinity. That's what it's showing. You did all this when you did polynomials, your what do they call parent functions, way back in pre-calculus algebra, okay? And when you did polynomials, you said polynomial functions always, for x large enough, it always goes without bound. Just determining whether it goes to plus or minus infinity. If the n is even, it always goes to positive infinity. If n is odd, they go in opposite directions. Negative infinity for negative x's, positive infinity for positive x's. And they follow the same pattern. Here's the cubic function, the raised to the 5th power, steeper here, flatter here, steeper there. 7th, steeper here, flatter here, steeper there. 9th, 19th, 29th, 215th, you know, it would just be, almost become a step function. These don't have limits. They're going to infinity. So why call them that? So I just have a little bit of issue with why we're even doing that. Okay. Now we have 1 over x. Okay. And this, one of these limits makes sense. The limit as x goes to infinity here, positive infinity is 0, negative infinity is 0. As x goes to 0, no limit. Just don't even say it has a limit. They say plus infinity, minus infinity. Don't even mess with that. Has no limit as x approaches 0. Has a limit as x approaches positive or negative infinity. That's going to be 0. And then you raise this to any power you want. If it's an even power here, they do like this. Still going to 0 here, no limit there. Okay? And so the point, if you have a horizontal asymptote, that's the limit. Okay. Now, this is probably worth your while, but you probably already did this when you did rational functions back in pre-calculus algebra, if you did that. Limits at infinity of a rational function. The asymptotic behavior of a rational function depends only on the leading terms. Now, some of the pre-calculus algebra text, in fact the one we use, says leading coefficients. It's always leading terms. I always change that and say leading terms. The leading terms of its numerator and denominator. Now, what do we mean by leading terms? The ones with the maximum exponents. Okay? So if you want to know what this is doing as x is going to positive infinity or negative infinity, look at the ratio of the leading terms. The ones with the maximum. Okay? If n is greater than m, basically divide this into that, it's going to infinity. There is no limit. If n is equal to m, then it's the ratio of these coefficients, because these cancel out. That's your limit. That's a horizontal asymptote. If m is greater than n, in other words, all these cancel out, you got a 1 over x, that's always going to 0. Okay? So, without messing around with limits, you knew this already. Okay? So if n is greater than m, there is no limit. If n is equal to m, there's your horizontal asymptote. That's the limit, positive or negative. That. And if n is less than m, that limit is 0. So basically 1 over x squared, x to the some power. Okay? So this is what it turns out to be. N greater than m, no limit. Going to infinity. N equal to m, less than m, this is going to 0. Same thing you did back in pre-calculus algebra without even messing around with the thinking in terms of limits. Okay. Now, they do give this as an example. This is example 4 in the text. And this is one of those cases in which you have two different limits, okay? And the reason for that, when your x's are positive, this is going to be positive, and this is going to act positive, okay? Because as x goes very, very large positive, this dominates these two. So this is the same as 12x over the square root of 16x squared, which would be 4x. So that would be 3. So there you are. Okay. If x is going negative, the square makes this still positive. So this is still going positive. This would be negative though, so you'd have a negative 12x over a positive 4x, so that gives you a negative 3. So this is one of those examples like that. Now, when will you ever see something like this? I don't know if you will. Are any of you heading into sort of a medical type area? You are. Okay, what's your major? Psychology? Pre-med. Okay, good. Biomedical science pre-med. So both of you may run into something like this. It won't be, the numbers won't be, this is called I think they call it a sigmoidal curve. This basically, not with the scale where it is now, moved this thing up here. And this would represent an epidemic. Okay? Maybe in psychology you're not going to get this, but you might have to deal with people who are in something like that. Initially, now again, don't worry about where the axes are. Initially, your prevalence, say, of a very bad infection, if it's not in the society, you basically are at 0. But once it comes, then usually infectious diseases, they start pretty slow, but then when enough do, you have a very rapid rise, and then at some point the whole population has been exposed, so you can't have it anymore. So you have 0 cases, very rapid rise in another. Ebola would be very similar to this. The flu might be similar, but a more gradual S. So the statistics you use when you're studying things like this, you convert this to logarithms, and you call this a logistic curve. So I think sometimes it's called sigmoidal or something like that, but basically they call it a logistic curve. And if you're studying the effects of that, you use a special statistical program, and basically you call it a logistic regression. You're using a logarithm and you're studying the regression. I know this because my wife works in the medical field, and she studies a virus called cytomegalovirus, and she uses logistic regression all the time in doing that. But this is basically what a disease curve looks like. This is not a disease curve because you don't ever have -3. But move that up and you would have something more like that. Okay. Again, you're not going to be tested on this, but I did want you to at least see what we're talking about when we're saying limits at infinity. Basically, you're talking about your horizontal asymptotes. Okay. Vertical asymptotes, if it's going to infinity, there is no limit. So why even mess with that? I don't know. Okay. That was 2.7. All right. I'm not going to assign any homework there, but if you are interested in this kind of stuff, and it might be applicable to your major, then, take a look at some of these. However, don't just skip through this, because, for example, for instance, example 33 is talking about the Michaelis-Menten equation, where an enzyme, again, a medical type thing, is combined with a substrate of concentration in blah, 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 and you follow a special pattern, and then you are interested in those horizontal asymptotes. When do you get within so far of your maximum? You do the same type of thing, just happen to think of this, when you're, say, medicating. You introduce a drug. Your bloodstream, you start out with none, and then it rapidly goes up, and at some point, then your body starts metabolizing and it comes down. So some things take a long time to do, so you can use this kind of analysis for all sorts of things. But anyway, they give who Michaelis was and who Maud-Menten was, and they you could write on either of those how they came up with this equation, applications of the equation. Maud-Menten was a Canadian-born biochemist, worked with enzyme kinetics with German scientist Leonor Michaelis. I wouldn't have known that was German if they said it. Leonor sort of sounds like it. She was also an accomplished painter, clarinetist, mountain climber, master of numerous languages. You may find her just an interesting person to write on anyway. Also in number 44, it mentions Einstein's theory of special relativity. If you can introduce some math into that, that's a potential paper topic too. And you can hardly talk about it well without math. Okay. Sorry, hit the wrong key. So let's go on to 2.8. We're rapidly approaching the end of chapter 2, which leads me to think I'll probably have your test ready for you on Monday. I think we'll finish chapter 2 by the end of class on Monday. I'll give you your take-home test for chapter 2. Good idea to be looking at these homework exercises. You'll see problems like this there. Okay. Let's get the slideshow set up from the current slide. Okay. Getting away from talks of infinity, let's get back down to a real world where we're not going to infinity anywhere. I really can't think of why they're showing this. Okay, intermediate value theorem is what the section's talking about. Roughly speaks of a continuous functions that cannot skip values. Okay, that's why they're bringing this up. If you're flying a plane, you take off, you are at a fairly low elevation for a while, and then when you get to go ahead, you can climb. At some point, you may level off. Maybe you run into weather, you decide to climb a little further, but there's some limit you can go to up there. But guess what? From your maximum height altitude, from where you take off to there, you're never going to skip any altitude in between. I mean, your plane just can't suddenly jump to a different altitude. You don't want it to. Okay. Really sick to the stomach on that. No, it just can't happen. That is a continuous function, and being a continuous function, it obeys the intermediate value theorem. What does that mean? You have two values here. There's always going to be at least one point in between there where you're at some intermediate value. Okay. That works for any continuous function. This, remember what we call this? Greatest integer function. The books love them. I can't think of why they spend so much time with it, but they do. They love them. This doesn't have, because that's not a continuous function. So there could be some value, there will be values in between here where the function does not take on the value, even though it has a value less than here, greater than there. It won't, because that is not a continuous function. Okay? Some of your piecewise continuous functions, they might have these, but there could be places where you would not find an intermediate value. Now this book uses this symbology for greatest energy function. Some other texts use sort of a double bracket here. Because a single bracket, when I first glanced at that, I thought they put absolute value. I said, that's the wrong function. But then I saw the little wings on it. Put a double bracket, it's pretty obvious that's greatest energy. But this book uses just a bracket, square bracket. Okay. So, I talked about it. Let's get a definition for it. The intermediate value function, theorem. And it's used so often, it'll be called IVT. So when you see IVT, intermediate value theorem. Okay. If f is continuous on some closed interval a to b, okay, that means it may be discontinuous somewhere else, but if it's continuous on some interval a to b, and, now this is also a requirement, f of a, this endpoint, is not equal to f of b, the other endpoint. Okay? That's required. Then, for every value m in between f of a and f of b, there's a different values. Okay? For every value in between those, there does exist at least one value c on the interval a to b, such that f of c is equal to m. Okay? So that's the intermediate value theorem in math speak. And it's pretty clear, hopefully. Might get you a little confused what's the intervals and what's the m's and what's alphas and c's and a's and b's. But let's go back and glance. Y'all got it? If you weren't paying attention to this, you may have missed it. They put some m's in here, okay? They didn't say, well, a and b. Let's just take a to be 0 and b to be 20. Okay? Those are values along your independent variable. This happens to be time, t, rather than x. Okay? So for any closed interval, 0 to 20, as long as f of 0, which appears to be 0 here, and f of 20 was 10,000 meters, okay? And this is a continuous function. You're in a plane. You haven't skipped any altitudes on your way up. You haven't jumped some. You can't do it. It's impossible to do. Then for every m in between, for any value c, that happens to be t0 here, in between a and b, 0 and 20, any value in there, oh wait, I'm sorry, take this back again. For any value in between f of a, 0, and f of b, 10,000, pick any number in there. It looks like they chose, that'd be 750. Let's just say 6,000, okay? Or whatever m here. There is at least one value between a and b, c, which is t0 here, where that function, if that's a continuous function, it's got to cross that somewhere. Everything between that. Now, it could have gone like this. It could have had more than one, but there's always at least one in between. One m value in between f of b and f of a corresponds to some c in between a and b. Okay? Now, on this one, there's absolutely nothing that's going to work at all. Because remember, even if you took an interval, say here, say from 1.1 to 1.9, that's an interval, it's a continuous function, right? What's the second part of that? F of a must not equal f of b. Any continuous part of this, that's going to be true. So you will not find any place here where intermediate value fits, okay? Because these are all constant functions where the function is defined if it's not skipping. any m you choose in between -1 and 3, choose a 1.5, you'll never have that because greatest energy function will never be a fractional factor. So, because this is not continuous function and has no interval that is a continuous function where f of a is not equal to f of b, then this will never fit the intermediate value theorem. So that's what the m's were. Okay. I think this is example 1. I'm not sure if I believe it is. Your text has a figure 2, not this figure 2, they threw in here, that helped describe graphically that the slideshow and the old text did not have. So this example 1 is your figure 3. It's a figure 2 here, but it's figure 3 in the new text. Oh man, that's going to be where we have to start next time, right? Is it? Yeah, it's 10. Okay. Sometimes mess up these times. So no new homework problems for 2.8. But let's just look ahead. 2.8 is a very short section. We'll finish this pretty quickly next time. 2.9, the formal definition of a limit. Boy, that's where my professor started. We didn't start with all this legal stuff to begin with. He dumped us right into that. We'll spend a little bit of time with that, and that's it for chapter 2. So basically 2.8 won't take us 15 minutes to finish this, and 2.9 might take us a little longer than that, but not. It's not very long at all. The new books, I think, put less emphasis on the formal definition than the older ones did. Boy, back in the old days, they lived by that. Then we move into chapter 3. So on Monday, we'll finish chapter 2. I'll give you your chapter 2 test, and then we'll begin chapter 3, differentiation. Good deal. Any questions? All right. Good deal. We'll have a good weekend. Working these math problems will make it good, won't it? Yes. Okay. James never made it in, and Jasmine didn't.